There is quite a mighty storm going on outside. G'day collaborators, and welcome to this time-lapse of a programming experiment that I did based off of a number file video that I had recently watched. You can find that video on the top right in that card thingy. The video presents to you this incredibly large prime number, which if you remove the leftmost digit, the number you are left with is still prime. And you can keep doing this until you're left with a single digit number. And I wanted to see if I could write a Python code to find all of these truncatable primes. As a part of the experiment, I wanted to make sure that all of the code that I used was my own, so I first created a method to determine if a number was prime by seeing if it divided evenly by the numbers less than it. If it divides evenly, then it's not prime, obviously. After getting that essential code out of the way, I needed to make the code to go about finding these truncatable primes. To create that code, I started with having an input, which is an array of already truncatable primes, and then it will add another number on the left of that number, and it will see if this new number is still prime. Essentially, the code is building these truncatable primes from the right to the left. So once I had finished the main section of code, and after I had refined it, I just let it run for a long time to see what results it would come out with, and I'm going to discuss that after the time lapse is finished. There's a pretty massive storm going outside. It's still going. It's insane. Anyway, so my Python script had finished. However, it finished way shorter than it was supposed to. In fact, it finished 108 digits shorter than it was supposed to. The largest number that I could find is this one here, which is like 8 trillion or something like that, or 8 quadrillion or something like that. And that number is actually found in this video over here. Yep, 899,765. 899,765, yep. So this number is actually found here. This number is in fact 108 digits away from this one, or 108 numbers away from the largest one. The reason why that's the case is because Python doesn't deal well with increasingly smaller numbers. You can see that this number here is obviously greater than 0 because it has a 1 here, but it just resolves that as 0.0, which is a bit of a shame. I wonder though, if I get this one and in fact ask if it is greater than 0, no, it's not greater than 0. So Python will immediately round this number off to 0.0, which is false, it's not correct. And so when we're dealing with 16-digit numbers, or even increasingly larger number, it just considers that this is not prime because it rounds off an incredibly small number to be just 0, which it will determine as not prime. So that is a limitation of Python and a limitation of my code at the moment. I'm sure there is a way that you can use Python to find all of the truncatable primes, but at this moment I am unable to find that. So yeah, so thank you so much for watching this this video. I appreciate you being here and I will see you in the next video. This is Quillo signing off. Goodbye and good luck.